We're going to look at section 14.6 today, which is directional derivatives and gradient vectors. And there's a whole load of stuff that I need to do before we can get to 4 and 5, which is what this is really about. So let me start with the first one. How do you find a two-dimensional vector, unit vector, in a given direction, angle theta? Okay, so let me remind you, and hopefully you will be able to tell me. Exact values. You can't do this. You must do exact values. You can't do this estimate. So this guy is 0, right? And this guy is 1. What's the exact value of pi upon 6? What's the sign of pi upon 6? Remember your unit circle. There's pi upon 6.
I think the sign is square root of 3 over 2.
And the
So I
cosine
have
would be
this.
1/2.
So we're going for the
sorry,
1/2 root 3.
Yeah.
Is that what we're going for? The sign is
1/2.
1/2. Okay. What did the sign equal? Okay. I'm not going to just write down what you say and then say, oops. Here we go. If you do the sign of pi upon 6, you're about to see a decimal. And that decimal is 0.5.
1/2.
Now, isn't this guy, as someone said, root 3 upon 2? Okay, let's go for the next one, which I think just because it's easier to remember. What's the exact value for pi upon 4? Sine and cosine, because they're both the same thing.
Root 2 over 2.
Yeah.
Agreed. Now, once you've figured out this guy correctly, can't you figure out this guy?
The sine
Don't
and
you
cosine
basically
switch.
exactly? And then the last one isn't that exact numbers, and they switch. So I guess if you can remember the pi upon 6 one, can't you kind of figure out all the others because of patterns and so on? You can always get the 0s and 1s. Your calculator will do that, right? Now that's only in quadrant 1, but quadrant 2, quadrant 3, and finally quadrant 4, aren't they the same numbers, but with some of them positive and some of them negative? For instance, if you were in the 4th quadrant, would the sines be positive or would the cosines be positive? Which one would be positive in the 4th quadrant? The sines or the cosines?
The cosines.
Agreed. All of them are positive in the 1st quadrant. Which one of these two is positive in the 2nd quadrant?
Sine.
Sine. Now, technically, it's all sine, tan, cos, but in our particular world, we're only caring about what these two are. So see in this quadrant here, aren't they both negative? Right. So if you needed to find the direction by a given angle, what they're saying here is, suppose that in 2D space, you were going at a particular angle of, say, pi upon 3. What would the two-dimensional unit vector look like? Well, the x coordinate typically would be r cos theta, but since it's going to be a unit vector, it's a little bit simpler than that. It's just cosine. And the y coordinate will be sine theta. So in this case, what would the vector making an angle of pi upon 3 look like? What would the unit vector, I should say? Well, it would be the cosine of pi upon 3 and the sine of pi upon 3. And since this is in the 1st quadrant, won't that be both positives? And since we have just spent a few moments figuring out what the heck this is, the answer we would get is √3/2.5, and that would be your unit vector in the direction of theta. Are we comfortable about how you can take an angle and create a unit vector that would travel in the same direction as that angle? Feel good? Okay, here's another one, and just to get us up and running. Suppose I wanted the unit vector u, and the angle is going to be 5/6 pi. Then it's going to be the cosine of 5/6 pi and the sine of 5/6 pi. Agreed?
Yeah, this is the two-dimensional
Now,
unit vector, right?
Yes, two-dimensional unit vector.
So it's only
So
going based off of
we
sines
need-
and cosines?
Correct. And the
Okay.
cosine goes for the x component and the sine goes for the y. Right. So what we need here is the exact value for these two guys. Now, although this is for quadrant 1, with a little bit of jiggery-pokery, couldn't we use this because the answers belong here to figure out who this is? What quadrant is 5/6 pi in?
Isn't that 2?
Or 2, sorry.
Second.
And because it's in the second quadrant, doesn't that make this positive? Right, this guy is a positive something, and this guy is a negative something. Typically, we don't write positives. Now, 5/6 pi, you might be really good at unit circles and know where it is. It's about here, isn't it? But what base angle does 5/6 pi correspond to?
The pi over 6, doesn't it?
Right. Yeah, and that's called the base angle. So what we're really going to do is pi over 6. Pi over 6. Do you see how I've reduced this question into this fella? And what do I know about the cosine of pi upon 6? The cosine of pi upon 6, where are you, is √3/2. And the sine of pi upon 6 is a half. And do you notice I got negative for this guy, but positive for that guy?
So with
Now,
these,
the reason
is
why we're doing
sine,
Mhm.
for these for these problems, I should say, is cosine always going to be the value of x and sine always going to be the value of y, like the unit circle?
yes. And
Okay, awesome.
And that's essentially what I'm saying here, right? And
Okay.
yes, you're right. And notice that there's no number at the front because this is going to generate a unit circle. Technically, if you go back to your trig lesson, won't there be an r cos theta here? The r would be the radius, and that would be for, I know, a vector. If I stick a 5 here, do you know I would do a vector in the same direction as that, but its length would be 5. And we don't want those. We just want unit vectors in these questions. So that's why we're just with that. I feel that I want to do one more, and then I'll move off of this particular question. The angle that we want to find a two-dimensional unit vector for is the angle of 3/4 pi. I want 3/4 is too small. Change my mind. Let's do 7/4 pi, which is over here, isn't it? Which means it's in the 4th quadrant. So when I look at this guy, it's going to be the cosine of 7/4, right? And it's going to be the sine of 7/4. Now, you can see in my picture that 7/4 is actually in the 4th quadrant, agreed? So which one of the two is positive if you're in the 4th quadrant?
Cosine?
So this guy is going to be positive and this guy is going to be negative. What is the base angle for 7/4 pi? The base angle is this angle in here, the one you make with the x-axis.
Pi over 4.
Right. And the fact that I can find its base angle means I can now refer to this table. So all you need to do is memorize this table and know how to get base angles, right? So it means you don't have to memorize like 20 answers. You only need to memorize about 5 answers, right? And so I think it's a little bit less work. And this is going to be sine, and we've already done this one. So it's root 2 upon 2 and negative root 2 upon 2. And that would be a unit vector in the same direction as that. So if you imagine someone doing a vector in 2D pointing that way, that's what this guy is, that's you. That would make an angle of 7/4 pi going anti-clockwise. Okay, we're comfortable now about a little sub job. If I give you an angle and say, what unit vector in 2D does that correspond with? These U guys, you feel comfortable about, you can now do them. You're only going to get angles that are standard angles, right? Ones that are in your unit circle. If somebody was silly and said, oh, theta is 2 radians or something, wouldn't you just grab a calculator and go cosine of 2, comma sine of 2 and just write down some messy decimal? That ain't going to happen. They're keeping the angles to be exact values so that everything is exact when you're finished. So I have a little shopping list over here of things that we were going to do. And we've just checked off, I hope, that one, right? So let's look at number 2. Unit vectors for 2 and 3-dimensional vectors. Right, I've just noticed something that might not be the case. When I draw vectors in 2 or 3 dimensions, the notation that I use is I put a little arrow above it. Some people, I think, put a funny little hat above it. Is that right? Do you put a funny little hat above it?
For unit vectors in physics.
Okay, so physics uses funny little hats. I'll call them hats. I know they're called carrots on my calculator, but I'll call them hats. And I use these. I'm not going to change now. I've been doing it too long in my life. And you've got to get used to other notation, because look at some of you are going to go to university, right? And there's a great chance you're going to get a European professor. You just look at the names and you can see either a Polish, a German, a French guy. They're guaranteed that they will use notation that's specific to where they came from. So you got to be able to say, oh, there's only one way to write a vector. There's only one way to do this. Get used to different letters of the alphabet. Thankfully, X, Y, and Z are the most common variable names in the universe, as far as I can tell. But there are lots of other idiosyncrasies about how to write a derivative, right? What kind of notation, right? You know, the partial derivatives have at least 2 notations that we are typically using, right? But get used to the fact that there are others. So I don't think a problem with me sticking with this. Does that mean you have to write that? No. Do you want to write your work in using this because that's what you're used to? Go ahead. It's the same thing, right? That's the bottom line. It's the same thing. Now, how do you get a unit vector? Well, this vector, actually, like X, Y, and Z, aren't U, V, and W the most common letters used when vectors are around? Right, that's just a notational thing. Right, let me get a unit vector here. This guy here, if you find its magnitude, which is 3 squared add 4 squared, this is Calc 3 stuff, you get the square root of 25, which is 5. So I wish I hadn't called that U now, because I want to use U to represent a unit vector. So the unit vector would be 1/5, this guy, or 3/5, 4/5. So to get a unit vector is very simple. Find the magnitude of your vector and divide its components by that magnitude. So the magnitude of this vector is 5. So you divide these 2 guys by 5. This vector is in the same direction, but its length is 1. So if you imagine this was the original, the unit vector would look something like that. Right, let me change a letter then. Stick a negative in. I want a unit vector, same direction as V. Oh, another notation I should just came to my mind. I use single vertical lines to mean the magnitude of a vector. Do some of you use a pair of vertical lines to mean magnitude? I mean, maybe I'm wrong. Have any of you seen this notation in physics?
Yes.
No? Yes, some of you. Is this a notation that some of you have seen instead?
As in
Right.
both.
Yeah.
Right.
Both.
So, hey, good. If the fact you've seen both now, aren't you comfortable with me sticking with that one then? I mean, I'm just going to stick with arrows to mean vectors and vertical lines to mean magnitude of those vectors. And, you know, I'm keeping my life simple by just having one notation. And you can mix and match the notation as much as you feel comfortable with. Now, in this case, it's going to be 1 squared add -2 squared, which is square root of 5. And so the unit vector of this guy would be that guy, or that guy, or
Shouldn't that be V, not U, is equal to?
U is going to represent the unit vector, and V is going to represent the original. So that's why I said up there, I wish I hadn't picked U. So the original vector can be V or W or whatever it is, but I'm going to restrict, anytime I write the vector U down, the implication is that it's a unit vector, right? And that's what we're going for. So it's still the correct answer, right? This is the unit vector. What we've got to look at here is 3 different ways of writing it down. You know, you can just leave the multiple outside this fraction. I don't like that myself. I don't mind this, because now it's a single vector, right? I prefer this. Why do I like this style points rather than this one? And I agree, I am being
radical is
nitpicky
on
here.
top? Because the radical's on top?
Yeah, exactly. Isn't there a rule way back in 94 that square roots should always be in the top if you can't avoid them? So you shouldn't leave things as 1 over root 2. Shouldn't you call them root 2 over 2, for example? Oh, and by the way, isn't that exactly what you do in trig? Don't we call it root 2 over 2?
Yes.
And not 1 over root 2? So I'm not the only pernickety person in the world. So I suggest strongly that you get into the habit of doing this, because if you do it and you don't need it, because, you know, they'll accept one of the inferior, I'm calling these inferior answers. This is much more helpful in case one day you get someone like me who's very pernickety and says, nah, make it look pretty. Right? So you're used to making it look pretty, so you don't think about it anymore. So, are we good with unit vectors of 2 dimensions? This is Calc 3 stuff, really. Let's do a vector V. Oh, and stick a negative in somewhere. Yeah. I want a unit vector in the same direction as this fella. Well, its magnitude is still the square of its components added together. Agreed? And so the unit vector is 1 over that, which is now going to become this guy, which is now going to become do you think I'm finished? Is this the ultimate?
You can still simplify it.
And yeah, I am being nitpicky, but really, that is the best answer. One of the things that mathematicians find causes problems, especially when we are trying to communicate with other mathematicians, is that if we are not very specific about how an answer should be written, we end up generating confusion, if that's too strong a word, but awkwardness maybe in responses. Because you do the work and some of you do it like this, and you do the work and some of you do it like this. And then you have to look at this and say, oh, I wonder if that's the same answer as this one. So can you imagine a German physicist is communicating with a French physicist on some numerical calculations, and the French guy sends, there's my answer. And the German guy has done it and he's got, this is my answer. Isn't there an awkwardness because they're not standardized? So when I talk about style points, what I'm really saying is we make the thing as pretty as possible, as nice and reduced as possible. And if we all do the same kind of style point rules, won't we all end up saying this? And therefore it's much easier to say, yep, we're on the right track here, rather than continually jumping around and having issues. Little side issue because it's came into my head and I want to show you. This is what happens when mathematicians don't get together and decide on a standard way to write something. What have I just written down here?
3.145.
And what have I written here?
3 times 145.
No, you haven't. In Britain, decimal points go in the middle. So if a British mathematician looked at that, he would be thinking you had just written down 3.145, and he would get really confused because he would wonder, where the heck did that decimal come from? That's a multiplication. Can you see how you can screw up communication even simply with decimals? Now, do you think the Americans are going to drop their decimal point, or the British are going to make this happen? Do you think you're going to join the British? I tell you, the British are not going to change to the Americans. Now, G, since you're here, do you want to tell me how a French person might say 3.145?
Don't they use a comma?
Yeah, they use a comma. So comma one.
Now, what are you going to think?
Yeah.
So what are you going to think when a French language mathematician writes that down? So whenever you think, oh, he's just been awkward, can you see what happens when you don't get awkward?
I have a funny story about that. Actually, I had like the first few maths that I taken way back in the days, like I was dealing with that for like the whole year, and it just screwed me up because I was used to this notation, like the 3.145. I was used to that.
Yeah.
And I had to change.
Now, do you think the French language community is going to change? No. Right. Now, if you are going to start communicating with foreign scientists, can you see the dangers that are inherent in that? So when I say let's make things style points, will you give me a little bit of leeway? Because at least if we all agree on those kind of things, isn't that part of the communication going to be much easier? So let's move on now and look at my next thing on my list. And it's a thing called the gradient vector. So imagine that you've got a two-dimensional function, 2x squared plus 4xy plus e to the xy, right? The gradient vector written down typically with that notation, an upside down triangle with an arrow. The arrow is indicating that this is a vector. Is that guy. And this thing called the gradient vector is going to be really useful later on when we start getting down to these things called directional derivatives. But right now we're just focusing on what they are and how you calculate them. Now in this particular example then, the first term of this vector is the partial derivative with respect to x. So that guy is 4x, that guy is 4y, and this guy is e to the xy times something. It is a chain rule, isn't it? So e to the xy times what?
Why?
Okay. And I just realized that I didn't give myself enough room, so I'm writing it again. Oops, here we go. And then you do it again, but with y's as your variable. You get nothing out of that. You're going to get 4x out of that, and you're going to get x e to the xy out of that. So this is the gradient vector for this function. It's really just a formula, isn't it? Plug and chug. Partial derivative of x goes first, comma, partial derivative of y goes second. It's not uncommon that you're going to evaluate a gradient function at a given point. Let's suppose I'm going to do it at the point 0, 2. Let's see what that would look like. 4 lots of 0, 4 lots of y times, that's 2 times e to the 0, which is 2, so that's this one. 4 lots of 0 plus 0, that's this one. I believe the answer would be 10, 0. So the gradient vector at the point 0, 2 is the vector 10, 0. Are we comfortable about how to find a gradient vector and how to evaluate it at one specific point, one particular x and y? Is that pretty straightforward? Do you need another one, or you feel comfortable just saying one? I say a nod, so we're good. You can also get three-dimensional gradient vectors. So let's suppose we have f, x, y, z, and it's x squared, x, y, z, plus y cubed, z cubed. Now the gradient vector you should not be surprised by this formula. Does that make sense? It's just a continuation of what a two-dimensional gradient vector looks like, right? Can you imagine then you could do a 10th dimensional function? Couldn't you find its gradient? And we're assuming that there's a natural order to the variables, right? X, then Y, then Z, right? First, then second, then third. Right, in this particular question, you get a 2x plus a yz, and then you get an xz, and then you get an xy plus 3z squared. Sometimes they don't write the x, y, z. Sometimes they just say delta f. In fact, it's not uncommon to call that the grad of f. So if you look at videos, instead of calling it the gradient vector of f, they just shorten that down to the grad of f. But it means the gradient vector of f. Are we good with gradient vectors? I think they're pretty straightforward, but that's me. That might not be you. Do you feel comfortable with what I did here?
Yeah.
Yeah. Now, don't make push you into a corner. If you don't feel comfortable, you know, I could do more. You're going to see them again anyway because they end up, oops, pointing at the wrong place. They end up coming up fairly shortly, right? So, a couple of thumbs up, I'm going for it. So, check that off my list. Directional derivatives. Now, this thing has a kind of clunky notation. A big capital D, directional derivative, a little funny vector u with an arrow above it, and that's there to represent the fact that you always do directional derivatives in the direction of a unit vector, which is why we did that unit vector stuff earlier on, right? Of some function. Now, here is the formula for calculating a directional derivative. It's the grad of f dot product with u. Remember dot products from Calc 3 and physics, whatever else you did, dot products.
I remember.
Okay, so what I'm going to look at are two special, no, let's rewind that, three special cases. The first case is when u is given by being told theta. The second one, and when u is a vector, that is already a unit vector. And the last situation is going to be when u is a general vector, just any old vector in the world. So the directional derivative is the gradient vector dot product with a direction vector that must be a unit vector. So let's put that package together and show you what it might look like. Suppose I have a...
What is that first special of the three? When u is given by...
When u is given by being told theta. So you're going to be given this one. So this is an example of this. Suppose you're given a vector x squared plus e to the xy. And you're being asked to find the direction vector in the direction theta equals pi upon 3 at the point 0, 1. So the question will have a function. You will have a point at which you're going to calculate the direction derivative, in this case at the point 0, 1, and you'll be given a direction. Now the direction vector in this, the vector here is given by the angle that it's making. But sometimes you might be told the vector v is 4, 5, right? Or the vector v is a half, a third, whatever it might be. So let's get the unit vector first. If the angle is this fella, isn't it cosine theta, sine theta? Remember we did that right at the start of today.
Yes.
What vector, right? What unit vector makes an angle of pi upon 3? And this is the unit vector. So it's going to be the cosine of pi upon 3 and the sine of pi upon 3. And if I can find my little guy that we did this on, there we go. Isn't the cosine of pi upon 3 1/2? and this guy is root 3 upon 2, and they're both positive. So step one.
I think it might be switched for pi over 3.
Cosine is a half.
Oh, shoot. Maybe I wrote it down wrong. Oh, yeah. Okay. Sorry.
Okay. No, I don't mind, because I do screw up a lot, and I'd rather you tell me. And, you know, if I made a mistake, we could fix it. But are we happy now that I do have a unit vector? Right. Now, what I'm now going to do is find the gradient vector, which in this case is what the partial derivative of x followed by the partial derivative with y. So this is 2x plus y e to the xy, comma x e to the y. And what I'm now going to do is evaluate the gradient vector at the point 0, 1. So it's going to be 2 lots of 0 plus 1 times e to the 0, comma 0 times e to the 1. And basically, what does that get me? Oh, it gets me a very boring answer. It gets me that guy. And now I can, that's step 2. Now I can finish the question off. Let's get the direction, the directional derivative. du of this guy is the gradient dot product with the unit vector in that direction, which is a 1, 0 dot product with a half root 3 upon 2. And dot products, you multiply the corresponding x's added to multiplication of the corresponding y's. And in this case, my directional derivative, technically I should have written this down, because it is at one specific point, right? Is at the point 0, 1, is a half. Whoa, what's up? What? Right, my wife has just turned up, if you're wondering where I've just gone.
Thank you.
You're welcome, Bubba got this. You know, you can get into Fort Knox easier than you can get into the shipyard. My wife needed her passport. Go figure. Right, okay, we call about this final answer, where it came from. Now, I guess if I was you, I'd be thinking, what is that half telling me? I mean, it's a number, right? But what on earth does it tell me? It's called a directional derivative. So it's a derivative of some kind, and its value is a half. And normally when we talk about derivatives, one way of looking at them is it's a slope of something, isn't it? Like the slope of a tangent line. So I want you to imagine, and this is purely imagination, I'm not saying this is really correct, but it'll get you the idea. Can you imagine that this function here was a surface that looked something like this? So just a hill. And at the point, where did we do? 0, 1. So at this point here, can you imagine that on the surface, there would be a point directly above 0, 1, right? It's got the Z coordinate. Can you imagine that at this point here, you went in the direction of pi upon 3, right? You went in that direction. on this point here, can you imagine going in that direction? If you traveled in that direction, if you sliced the shape in that direction, wouldn't you get a curve? Right. Can you imagine slicing the shape like it was a cake? Wouldn't there be a curve that would cause by that direction? The slope of that curve at that point is a half. So that's what you're finding when you're finding the directional derivative. You're finding the steepness of the hill if you walked in that direction. So can you imagine in that point, if I went straight up the way, it'd be quite steep. If I went kind of horizontally, might it be a zero, right? And if I kind of went and changed my direction in another way, couldn't I actually have a negative number because I'm walking downhill? So what a directional derivative does is it tells you how steep a hill is, right? What kind of gradient are you moving in any given direction theta. Now, can you imagine at certain points in this curve, won't some parts of the hill be steeper than others? Right. And one of the things that you might be interested in is what is the steepest part of the hill, which we tend to transform into what is the greatest magnitude of the directional derivative. And very often that can be helpful, because if you imagine this not representing a surface, but maybe representing, oh, I don't know, a magnetic field, wouldn't it be interesting to know in which direction the greatest increase in magnetism was happening, or the greatest increase in airflow, or whatever it is that you happen to be measuring? That's kind of, yeah, that's a very natural place, I think, for me to finish. When we come back on Friday, that's not Friday, Monday, I should say, we're going to finish off doing some more practice at these, and then we'll look at how you find a maximum rate of change and the direction in which this maximum range of change occurs. And that's pretty much what directional derivatives' job is. Right? To tell you how steep a surface is at a given point going in a certain direction, and to find the steepest direction in which you can travel. Any questions before we call it a day?
I think yesterday you said you would do number 14 from the chain rule. Could you go over that real fast?
Perfect. Right. Do you have a copy of the number the question handy?
It was that V equals IR,
Oh, yes.
the electrical circuit.
Yes, V equals IR, and they had a whole load of stuff with that. Okay, let's get that guy sorted out. If you've got other things to do, guys, I say hi before you leave, and you'll just have to watch the end of this video. For the rest of us, I'm going to do it right now. Hopefully it won't take more than a few minutes. Yeah. I have no memory at all, so I'm glad someone's on top of it.
Thank you, Professor. See you on Monday.
Okay, see you Monday. Okay, so we are looking at, hold on a few moments. Edit, what number was that again? Probably the last one.
I can't remember the exact number,
Yeah,
but
it's 14. I got it in front of me. Yeah, here we are. I've got all the details. I won't zoom in and out and show you, but we're being asked to find the rate of change of the current. So we're being asked to find di by dt. So the first thing I'm going to do is actually change this formula around so it looks like that. Now, how am I going to find that guy? Well, I'm going to find di dv dt plus di dr dt. Do you see where the chain rule's kicking in? Cancel them, you get this guy. Cancel them, you get that guy. Great. Now, each of these things are numbers that they have already told me somewhere or other, and I'm just trying to find them. If you differentiate this guy with respect to v, right? So if you do a derivative of this guy with respect to v, you get 1 over r dv by dt. And if you do it with respect to r, you get negative v over r squared dr by dt. And then I go looking for things. I've been told that dr by dt is 0.04. I'm being told dv by dt, which is this guy, is, make sure I don't screw this up. In my question, it's negative 0.06. I'm being told that r is 458. And 458 squared. And they also told me, unfortunately, not what I wanted, but they told me I is this number and R is this number. Does it not make V then, whatever these two things are? So I now also know what value V is. So it's 0.07 times 458. So that's 32.06. So I put 32.06. So this is where I'm going to leave it. Isn't that just one big ugly calculation? And you round off that answer to 6 decimal places. Now, what you're going to find when you do your homework question is that this is still correct, right? This is still correct, but the numbers for these things will not be necessarily the same numbers I've got. You might find out that that's negative 0.02 and that this is 500. But that's just a matter of plug and chug, right? You plug in your numbers to get your answer.
All right, thank you.